All right, so let's start. We'll continue today with what we were discussing in the last lecture regarding output swing. And so one of the results that we had seen earlier is that no matter how much input voltage you apply, whether it's small or large, harmonic distortion is something that is always there. And as an example, for example, we have applied 5 millivolts here to the input, and 5 millivolt signal also results in harmonic distortion. We get a peak-to-peak voltage of 0.91 because the gain of the amplifier is roughly 90. So 10 millivolt peak-to-peak input will result in 900 millivolts of peak-to-peak output. There's a harmonic distortion of 4.8%. And note, this is the fundamental here, second harmonic here, third, fourth, and all that. So the most dominant component of harmonic distortion is the second one. Note that the scale is a log scale, and the second harmonic distortion is the most dominant one. You can see, and the third harmonic distortion that you can see is at least one order of magnitude lower. It's a log scale here, so if you compare the magnitude here versus the magnitude here, you can see one order of magnitude lower, the third harmonic distortion here. So if you are doing a approximate analysis, you need not calculate HD3 and HD4 and HD5 and all that. You may just concentrate on the second harmonic distortion, HD2. The other thing is, note that I've applied 5 millivolts. We get an output voltage of 0.91, harmonic distortion of 4.8%. If you want a higher output voltage, if you want more than 0.91, then obviously you'll have to apply higher input voltage here. As you apply higher input voltage, you'll get higher output voltage, obviously. But then, as you apply higher input voltage, note that as you apply higher input voltage, there would be larger value of base emitter voltage. Larger value of base emitter voltage, which means more nonlinearity. So what would happen is, harmonic distortion would also increase with Vs. Alright, so that's one can get a higher swing here, but higher swing would require a larger value of Vs. A larger value of Vs means more base emitter voltage, small signal base emitter voltage, more harmonic distortion. So harmonic distortion is a very important part of output voltage swing. A discussion of output voltage swing without harmonic distortion is at least for an amplifier like this, is not that meaningful. We had seen a result like this for maximum voltage swing, which neglected harmonic distortion, which took a very simplistic picture that the sinusoid that you see here is a perfect sinusoid. The positive swing and the negative swing are equal. We saw in the last lecture that one of the consequences of harmonic distortion are that the positive swing is quite different from the negative swing. The sinusoid is distorted. Now, as I said, we took a very simplistic picture of a perfect sinusoid. And based on that, we said, well, if we bias it in the middle, we'll get maximum possible swing, right? If I set here, for this analysis, I'm neglecting VC sat, assuming it to be small. So we said that VCEQ is approximately equal to VCC by 2 in the middle. Then we'll get a swing which is equal to VCC by 2 here and VCC by 2 here. That's what we said. But we know that such a swing, this is not the real picture here. My sinusoid is distorted. Now, let's just see what is the consequence of it. Remember just the previous discussion that if you want a higher swing, you'll have to apply a higher voltage, and higher voltage would imply higher harmonic distortion. So to get a swing of VCC by 2, how much input voltage do I have to apply? How much input voltage? If that input voltage were small, maybe harmonic distortion would be small. So let's calculate here. This is an expression for gain that we had calculated. AV, there are different ways in which you can write. I've written only the magnitude part. You could have written ICQRC divided by VT. ICQRC is nothing but VCC minus VCQ by VT. Alright, so if I'm trying to attain this condition, VCQ is VCC by 2. So if I put here VCC by 2, so the gain under this condition will turn out to be VCC by 2 VT. This is the gain that I will get if I bias my transistor right in the middle. I'll get a gain of VCC by 2 VT. All right, gain is output voltage divided by input voltage here. So output by input is VCC by 2 VT, gain. And we know that for this kind of biasing, VOM we are expecting equal to VCC by 2. So if I put here VCC by 2, I'll get what value of VS or input voltage do I have to apply? It turns out to be VT. So note that this analysis is telling you that bias in the middle in order to get a swing of VCC by 2. Fine, VCC by 2, that implies a gain of so much. And that implies that I have to apply an input voltage as large as VT. That's a very large voltage, 26 millivolt here. We know that if you apply such a large voltage, you get very, very high harmonic distortion here. So this picture, what I'm trying to point out to you is a very limited picture because it's neglecting harmonic distortion. For example, if I did take an amplifier like this and I applied Vs equal to Vt equal to 26 millivolt, look at what I get here. Clipping here, distorted, totally distorted here. This picture is telling you that you'll reach VCC and VCC somewhere over here. You fall short of VCC by almost, this is 4.29, VCC is 5 volt. You don't reach 5 volt here. And on the negative side, we had hoped that it would just touch the this thing here, 0. Is not just touching, you're seeing that is highly clipped. So that picture is not valid. Why? Because it's just simply neglecting distortion. It's not taking distortion into account. And therefore, one is not getting the right answer. Even if I apply 26 millivolt here, 18 millivolt. Even now, 18 millivolt. So note that to get VCC by 2 swing, we had to apply 26 millivolt. And that's completely distorted. If I apply a lower voltage, 18 millivolt, I get a swing of 3.6 instead of 5. Even now, the distortion is 6.9%, 16.9%. Fairly high distortion. If you look at the positive amplitude, negative amplitude, they're quite different. All right. So the thing is, then we have to take, when we are talking about harmonic voltage swing, we have to talk about harmonic distortion. It's not enough to say I get a swing of so much without talking about harmonic distortion here. All right. So this is something that we had seen earlier. Now, so this is the picture that we had earlier, right? A perfect sinusoid, which gave us that bias in the middle, VCC by 2, to get a maximum swing. The picture that we are seeing now is a picture which is more like this here. The positive swing that you see here is much smaller than the negative swing here. It's a distorted sinusoid. So the picture is quite different. It's not this. It's not a symmetrical sinusoid here. This is more like the sinusoid that I get when I apply an input here because of distortion. So now the issue is, with a picture like this, how should I bias? Should I bias in the middle? Should I bias somewhere else? How should I bias to get a good swing? Now, our VCC by 2, when we arrived at that we should bias in the middle, it was based on these two facts here. That my output voltage swing is either limited by transistor going into saturation, which was the first part, VCQ minus VCSat, or my transistor or the output voltage touching the ceiling here of VCC. It was based on these two facts here, and we equated this with this, and then we got VCC by 2. Now we are noticing that yes, my transistor does reach saturation. In fact, if you go back into all of that, you'll see it does touch saturation, but it never touches the VCC part here. So what is flawed is this part here. This is flawed here. I will never reach that ceiling of VCC here. Before I reach the ceiling of VCC, I start getting heavy distortion. Okay. So what we have to do is, obviously from this picture you are seeing that VCQ equal to VCC by 2 is not a good design for maximum output voltage. You're not getting it. If you bias it like this, it requires a very high input voltage and you don't get a swing equal to VCC by 2 here. So how do we go ahead and develop a better equation? Well, what we have to do is bring in harmonic distortion into our picture here. All that, why we are deviating from this particular picture is because of harmonic distortion. Positive swing, much different from negative swing here. So we have to bring in harmonic distortion into our picture, and we have to bring it into our consideration of maximum voltage swing. Okay, so let's do that. So this is our amplifier, and we said, note, this is the way the amplifier works. Applied voltage modifies VBE, VBE modifies IC, the modified IC or the change in IC flows through RC and develops an output voltage here. Distortion is occurring at this point here. This Vs directly goes to VB, no problem. VB causes changes in IC. This is where the distortion occurs. IC flows through RC. That's a linear relationship, Ohm's law. No distortion here. So this is the critical part here. How does my base emitter voltage change my collector current here? So that's the place where all the distortion is occurring, and we need to look at that in detail. So if we do that, we know that the relationship between collector current and base emitter voltage is an exponential relationship. So for example, in general, I will have a DC current plus a incremental, maybe an AC current here, which is equal to IS exponent DC voltage here, and an incremental or small signal voltage VBE here. So this additional VBE, which may be sinusoidal, is what is causing the sinusoidal IC to flow here. So what we want to do is, we want to look at now relationship between this incremental IC, or small, is no longer small, so incremental IC and incremental VBE, and not just approximate that relationship into a linear one. So easily one can rearrange this equation, IC equal to ICQ, exponent VB by VT minus ICQ here, because note that when the small VB is absent, VB is 0, then IC is also 0, and ICQ is simply IS exponent VBEQ by VT. Okay, so this allows us to write in this manner here. Next, what we are going to do is we want to calculate harmonic distortion. So we'll say our input is a sinusoid. So input Vs that I am applying here is same as VBE, is equal to some magnitude VB0 sine omega t. So we'll take this, plug it here. Now, just for convenience, I'm going to write VBE0 by VT, because note that what matters in all of this is the ratio, VB by VT here. So I'm going to write this as M just for convenience. So I can write here IC by ICQ is exponent M sine omega t minus 1. The same equation written down here with the change that we have put this value here and define VB0 by VT equal to M. Alright, so that's the, here. This is a DC current, is a constant. And IC is going to be, we expected it to be a ideal pure sinusoid, but it's not going to be because of this relationship here. Let's expand this, IC by ICQ. So if we expand this, we get, there's a 1 here which cancels M sine omega t plus the usual expansion of a exponent. We'll get higher order terms as well. Okay. All right. So when we expand it, we can take, as I said, I showed you a picture where my second harmonic distortion was the most dominant one. The third and the fourth are there, but not as important. So I'm not going to, at least in analytical calculation, I'm not going to consider that. So sine square omega t, all of you can know the expansion of sine square. We can write it in terms of 1 minus cos 2 omega t. When you do that, you get a DC term also. I've neglected that. The fundamental component is m sine omega t. The second harmonic then is m square by 4 cos 2 omega t. Plus there are other terms. We are doing a simple analysis here. So note that this is my IC, which we expected it to be a pure sinusoid, but we have additional components also. And remember, the distortion is occurring because my collector current itself has harmonics in it. Collector current has first harmonic, second harmonic, third harmonic. So that's the reason why my output voltage has harmonics here. So whether you talk about output voltage or you talk about collector current is the same thing, because the relationship between the two is a linear relationship. All right, so that's what I was telling you. The third and the fourth and all that are much lower. I need not consider as a first order approximation the other terms here. So how much is the second harmonic distortion then? The ratio of this term and this term. So second harmonic distortion, HD2, is basically equal to the amplitude here, m square by 4 divided by m here. So we get m by 4. Now m was the ratio of the amplitude of the sinusoid, VB is 0 by VT, input amplitude here. So we go ahead and plug it here, HD2. And in terms of percentage, I can multiply by 100. Usually harmonic distortion is quoted in percentage. So I multiply by 100. So we get VB0 by VT into 25. So that's the harmonic distortion that I'll get in my amplifier. Now note, as a very simple rule of thumb, you know that VT is 26 millivolt at room temperature. So 26 is approximately equal to 25. So you could cancel these two. So how much is the roughly harmonic distortion that you'll get? The amplitude of the input in terms of millivolts. If I'm applying 5 millivolts here at the input, I'll roughly get 5% second harmonic distortion. It may be 4.8 and all that, but as a first very simple rule is, if you apply 5 millivolt, you'll get 5% harmonic distortion. Go back and see, something similar is what we are getting. 5 millivolt, we applied, we got 4.8%. Total harmonic distortion. In another case, we applied 18 millivolt, we got 16.9, close to the 18 itself. So harmonic distortion, first order is approximately the same as the input that you apply here. Okay. But we want to be a little bit more accurate. So we'll take this equation. HD 2 in percentage is VB by VT into 25 here. All right. So even though I'm doing I've derived this equation by not small signal analysis, but by looking at a more exact expansion of my relationship between current and voltage. If I want to relate it to output voltage, well, output voltage is approximately related to input voltage through AV. When because this relationship is based on linear relationship, small signal, so it's not strictly valid, but we'll still, that's why we have put the approximate sign here. So we'll take it anyway. VOM is approximately equal to AV times VBE0. We'll take VB0 out from here in terms of HD2 and write it here that VOM, if you want HD2 to be less than a certain value, then VOM must be less than or equal to VT HD2 by 25 into AV. VOM is simply AV times VB0. So take VB0 out from here, multiply it together. There need not be a less than sign here. You can keep equality also. And then what we do is we put in the value of AV, voltage gain. Voltage gain is, one expression is ICQ, RC parallel RL. If RL is there, if it's not there, ICQ times RC divided by VT is there. The VT cancels and we get an expression for voltage gain. That my voltage gain, depending on the harmonic distortion I'm willing to tolerate, is this particular value. There should be an equality here. So if you are looking for 10% harmonic distortion, you put here 10%, and whatever is ICQ, RC parallel RL, that will give you one constraint on VOM. That is the voltage swing that you'll be able to get. If you're willing to tolerate higher value of harmonic distortion, you'll get higher swing. Okay. All right. So that's another equation that we have arrived at. A limitation on output swing determined by how much harmonic distortion you're willing to tolerate. Okay. So let's continue with this. So is this equation still valid? Well, yes, this equation is still valid because we saw that, if I apply a large enough input voltage here, my transistor does go into saturation. And so this is still a valid equation here. But we saw that this point never reaches VCC. So we got rid of that. And instead of that, we have another equation. VOM should be less than or equal to ICQ RC parallel RL HD2 by 25. So we replace that. It doesn't touch the ceiling of VCC. Even well before it touches the ceiling, the sinusoid gets distorted. And so we have substituted this particular equation, taking into account harmonic distortion. So you can see that there is still a sort of a trade-off, because note that if you make VCEQ very low, now what are you doing? If you make VCEQ very low, let's forget about RL for a moment. If you make VCEQ low, then if VCEQ is low, then ICQ times RC is large for a fixed VCC here. So low VCEQ, ICQ RC may be large, and ICQ times RC and whatever harmonic distortion you have chosen, this value may turn out to be large and this value may turn out to be small. because you've chosen a small VCQ. So your swing will get limited by transistor going into saturation. On the other hand, if I've chosen VCQ as a large, this may not bother me. VCQ large means the drop ICQ RC is small, and so this term tends to become small, and therefore my swing is limited by harmonic distortion. So you can see still I have to play around with VCQ. Where do I put VCQ? If I put it too low, then this will bother me. If I put it too high, then this will bother me. So and both of them are dependent on the choice of VCQ. ICQ RC is nothing but VCC minus VCQ. So both these terms are determined by a choice of that. So what we have is a modified form of expression. What we are saying is my maximum voltage swing, whatever I can get, is either determined by this, if this is lower, or determined by this, whichever one is lower. Okay, for a value of HD2 that you are willing to tolerate. It's up to you to decide how much harmonic distortion I can live with. If my application says 5% harmonic distortion, you have to put 5% and see which one is smaller, and that one will determine your output swing. Okay. Now, if you want to design for maximum swing, how do I bias my transistor for maximum swing? Well, I just showed you that these two terms they go in opposite direction. A higher VCQ makes this higher, a higher VCQ makes this lower again. So again, the same balancing act. For a maximum swing, what you do is you make the two terms equal. Make the two terms equal. And from there, calculate what is the value of VCQ, which is optimum here. So what I've done is, there is a VC sat. So to keep the expression simple, I've neglected VC sat, ignored that. And then what we find is that for maximum swing, VCEQ is VCC, just a rearrangement of all of that here. Note that keeping in mind that ICQ times RC is basically VCC minus VCQ. So a rearrangement of this equation allows us to write the design for maximum swing. VCEQ is VCC 1 plus RC by RL 25 by HD2. So now our design for maximum swing takes into account harmonic distortion. The earlier picture was neglecting harmonic distortion here. Okay. So this is our design for maximum swing. We can simplify it further. I've been, for generality, I've kept both RC and RL. Let's say if RL is very large, this simplifies further. If RL is very large, this term becomes 1. So we get VOM equal to VCQ, VCC 1 plus 25 by HD2% for RL equal to infinity. Now note that this is a general expression. If you put here HD2 25, HD2 almost equal to 25%. Now remember what I said? I said the harmonic distortion is almost equal to the input voltage that you apply. So if I apply an input voltage which is 25 millivolt, I will get harmonic distortion of around 25% roughly. So 25 will cancel, and I'll get 1 plus 1, I'll get VCC by 2. So our earlier result which said bias it in the middle to get maximum swing, well, you will get that result provided you're willing to tolerate a very high value of distortion, almost like 25%. If you can tolerate that, well, go ahead and bias it in the middle. VCEQ should be VCC by 2. But for example, if I can tolerate only 10% harmonic distortion, you go ahead and put 10% here, and you'll get VCQ is 1.43. You don't bias in the middle, but bias it closer to 0 here. So you get 1.43 is an optimum bias to get maximum voltage swing with 10% distortion. If you want even better distortion, 5%, so you go ahead and put here 5. So 5 and 5, 25, so you'll get 5 here and 6 here, and you'll have to bias it somewhere close to 1. So where do you bias to get maximum voltage swing actually depends on what this expression is telling you is how much HD2 are you willing to accept. 5%, 10%. If you don't care about harmonic distortion at all, go ahead, put 25%. You're okay with a very distorted sinusoid. Put here 25% here. 25 will cancel, and you'll get VCC by 2. So that's so this equation neglected RL. If you want to keep RL into picture here, if there is a RL here, then this is the right way of biasing to get maximum swing there. And prior to that, the general expression for calculating voltage swing in any amplifier, then an amplifier like this, is actually evaluating VCQ minus VCSAT, evaluating ICQ, RC parallel RL, HD2 by 25, these two terms. Whichever term is minimum will decide your whatever is the swing that you'll get. So either this touching the floor here, transistor going into saturation, or harmonic distortion. Okay. Now, so we have now a improved expression which is here, which tells you how to calculate the bias and what kind of swing that you can get here. Now, last lecture we were seeing that if you put an emitter resistance, what it does is it puts negative feedback into your circuit and it drastically reduces distortion. So this entire formula and all that we have calculated is when there is significant distortion. If there were no distortion, if there was no harmonic distortion, remember what the optimum bias would be? Just VCC by 2. If HD2 is not a consideration, not that, then you'll bias it in the middle. So now that we are saying, if I take an emitter resistance, small emitter resistance, the small emitter resistance puts in negative feedback and reduces harmonic distortion. So our earlier picture that bias it in the middle may be okay here. So look at this particular case here. So this amplifier here, we bias it almost in the middle. This is almost 2.5. Here starting point 2.5 here. And we bias in the middle and apply a voltage with 60 ohm emitter resistance here. Note that it reaches fairly close to 5 volt here. This is 4.6. And here is going into saturation here. And giving you a swing of very close to the ideal value of 2.5 or 5 volt peak to peak. Why? Because now we've been able to reduce distortion using this emitter resistance here. So in this case, biasing it in the middle, VCQ by VCC by 2 is a good bias point. Because why? Because we have all that thing that we discussed was because there was harmonic distortion. By putting a 60 ohm resistor here, we have been able to reduce harmonic distortion significantly, and thereby this becomes a good bias point. So, but what is the price that we have to pay? This transistor earlier had a gain of 90 or so. By putting the 60 ohm resistor, we get a gain of 16. Okay, so that's the price that we have to pay. So if you are designing this amplifier without an emitter resistance, and you want to know swing and all of that, how to design, you have to take these things into account. On the other hand, if you're willing to sacrifice gain, put a little bit of emitter resistance here, then harmonic distortion is significantly reduced. Biasing it in the middle is a good strategy. Okay, so it all depends on which configuration are you using, without an emitter resistance or with emitter resistance. If your goal is to get very high gain, I'll not put an emitter resistance. And on top of that, if you're looking for still some amount of swing, then go ahead and evaluate it in this particular manner. Bias it according to these equations here. All right. So this emitter resistance that you see here is a very, very useful quantity here. Because if your goal is to get swing, there's nothing that you can do with this particular configuration. I cannot change RC, RB, no matter what you do, you'll never be able to get a good swing with low distortion. Note that if I want 5% distortion, I put here 25 by 5, I get a factor of 6, 5 divided by 6, I get less than a volt swing. I can't do anything with this configuration here, no matter how you design. With 5% distortion, you'll only get 1 volt swing. But look at this one. With 5% distortion, I'm getting almost close to the maximum swing that I want. So if swing is your interest, output swing, then this is a much better configuration. So now, how do you combine best of both the worlds? Well, maybe what you should do is cascade 2 amplifiers. So cascade 2 of them. In the first stage, you build up gain. You consider you build up gain here. Let's say I have 1 millivolt signal here, very small signal here, and I want to amplify. So the first stage has a gain of 100. So 1 millivolt takes it to 100 millivolt. So the swing, if you apply 1 millivolt and the gain is 100, so all you get is 100 millivolt output. And 100 millivolt is okay. I'll get very low distortion. And then in the next stage, after that, where you want the swing, so your signal is 100 millivolt, you apply now, use an emitter resistance to get the swing. All right, so this stage sort of specializes in getting you a good swing. It gives you a gain as well. It's not that there's no gain. And in fact, if you're bothered about 5%, I could have reduced the gain even further from 16 to maybe 3 or 4 and obtain more linearity, even lesser distortion. So you sacrifice gain here and build the gain in the previous stage. And in this stage, you try to get your a good swing with low distortion. All right. Now we are seeing that this particular stage is then a very useful stage. A stage where you put a little bit of emitter resistance is a very useful stage here. So what we want to do is, fine, we have seen that it reduces distortion. What does it do to other things? We have been seeing that it reduces gain. Okay, so let's look at this particular stage in a little bit more detail here. So this is the stage that we have here. It's, just to remind you, its gain is GMRC. Its input resistance, RB parallel RPi, we'll take most of the time RB much larger. So input resistance is RPi, VT by ICQ times beta here. Output resistance is simply RC. And we said these three are related together by this relationship here. You can trade one with the other based on this particular relationship. Well, what if I put a little bit of RE here? What happens now? So to calculate what happens now, I have to redraw the small signal circuit with an RE here. And I'm not going to go into details. You should be able to calculate. What I can say is I'll write on the result. AV0, note I'm making a little bit of approximations here. Please do the derivation and see where the approximation is, okay? So AV0 is minus GMRC, same gain, but divided by a term called 1 plus GMRE. Gain becomes smaller by a factor 1 plus GMRE. Output resistance remains the same. When I look from here, the output resistance is limited by RC. So output resistance is the same. Input resistance is RB, parallel RPi is so much here. Again, assuming RB is much larger, we get RPi 1 plus GMRE. So it's interesting, if you look at, if I'm putting RE in the emitter, what it's doing is, it's reducing gain by a factor 1 plus GMRE. It's reducing gain by this factor, leaving output resistance unchanged, and increasing input resistance by 1 plus GMRE. So it's decreasing the gain and increasing the input resistance. If I multiply them together, AV0 multiplied by Rn divided by R0, I'll still get the same thing. I'll still get the same relationship. So one way of looking upon this particular stage is what? That, you know, we are saying that AV, Rn and R0 are related together. If you're not happy with a certain gain and certain input resistance, certain output resistance, you can trade one with the other. Putting an emitter resistance is allowing you to carry out a trade-off in one particular manner. If you earlier this was giving you a gain of 100 and a certain input and certain output resistance, well, by putting a suitable value of emitter resistance, I can get a gain of 50 and double the value of input resistance. This trade-off I can carry out by putting a RE here. And the plus point is that when you put an RE here, it not only allows you to carry this trade-off, but it also improves linearity. It reduces harmonic distortion. Okay, so it allows you to do that as well here. So this particular example will tell you how much RE do I have to add to reduce gain. Okay, so let's very quickly look at this particular example here. Let's say I bias it at 1 milliampere. I take this amplifier, bias it at 1 milliamperes. GM is ICQ by VT 0.038. Now note that if I put RE equal to 26 ohms, GM times RE turns out to be 1. And gain becomes GMRC by 2. Input resistance becomes 2 RPi. Output resistance remains the same. So it's showing you why this resistance is so small. You can see here, all I need to do is GM times RE has to be significant. And because GM, you know, when I typical bias 1 milliampere, GM is so large that RE also is, you know, to make it 1, RE does not have to be a very large quantity. A very small quantity of 26 ohms allows you to get GMR equal to 1 and reduce gain by a factor of 2. Now, when you're reducing gain by a factor of 2, input resistance becomes double. By the same amount, input resistance also increases. Okay. So as I was saying, if you're, and this relationship still holds. AV0, Rn by R0. So what we have done is, we have reduced gain by a factor of 2, multiplied Rn by a factor of 2, and left R0 unchanged. Alright. So if you're wondering, so let's take an amplifier like this. So it gives us a gain of 90, input resistance of 1.32, output resistance of 1.2. So I'm telling you that, well, I can carry out trade-off. I can reduce gain and increase input resistance here. Well, you may be wondering, I can do that here as well. Suppose I give you an amplifier without putting a emitter resistance. Can you decrease the gain by a factor of 2? How would you do that? Decrease gain by a factor of 2 and increase input resistance by a factor of 2, leaving R0 unchanged. Which means if I leave R0 unchanged, I have to leave RC as it is. Now, how do I decrease the gain by a factor of 2? What do I do? Note what is the gain? GMRC, or what was the gain for that first stage? GMRC, which is nothing but ICQ RC by VT. If I can't touch RC, I have to touch ICQ. So reduce ICQ by a factor of 2. So I can do this. I can reduce ICQ by a factor of 2. How do I reduce by a factor of 2? Well, base resistance that you see here, this is biased through this. I'll double it. So look at this design. I make it 440K. ICQ approximately becomes half. Gain becomes 45 half. Input resistance becomes double. 1.32 becomes 2.6K. R0 is unchanged. So, I've carried out a trade-off between gain and input resistance. Half the gain and multiplied the input resistance by a factor of 2. So there is a very simple way of carrying out the trade-off by simply altering the value of ICQ. But I'm saying there's another way of doing that. Another way is this one, where I kept everything the same, 220, 1.2, everything is the same here. Same bias point. Note 1.93, 1.95. Same bias point. But what I did was I attached a small resistor here. And what do I get? 44.3, gain half, input resistance double, output resistance is the same. So I can do that also. I can carry a trade-off by putting an RE here. Or I could carry a trade-off between the two by reducing the current. What is the advantage of this one? Well, in this case, I altered the bias point also. I had to reduce to get higher input resistance. I had to reduce the current. And reduction in current also altered VCQ. So what it will do is, it will also modify other properties which depends on the bias point. While in this case, I carried out a trade-off without modifying the bias point. Bias point is still the same. And VCQ is still the same. And we carried out the trade-off between gain and input resistance by putting this small value of RE here, 13.5 ohms. It's because it's so small, note that 13.5, that compared 13.5 compared to 1.2K and 220K, it doesn't alter the bias. Doesn't alter the bias. When you're calculating the bias point, you're writing a KVL starting from here, going down here to calculate the base current. Well, you start from here and go down here. 13.5 will not do anything as far as the bias point is concerned. But it plays a huge role in the small signal analysis here. Okay. And the other thing that you obtain is high linearity. This circuit gives you high linearity, reduces harmonic distortion. Now, if you compare these two stages, look at these two. Both these stages give you same gain, same input resistance, same output resistance. And I'm saying this stage gives you higher linearity, lower harmonic distortion. Well, remember a general statement, something has to come at the price of something else. You can't get it for free. Apart from the fact that I've used a small resistor here, so I've used an extra component. Note the difference between the two. Same gain, same input, same output. Much better linearity here, much lower harmonic distortion. What is the other major difference? Look at ICQ, 1.93 and 0.98. This draws half the power as compared to this one. The power that I take from the supply, if supply is 5 volt here, the power that I will draw is 5 volt multiplied by ICQ. I take twice the power here as compared to this. So what you're saying is that's the price that you are paying, a higher power dissipation as compared to this particular circuit here. Okay, apart from the fact that one extra component is something that you're using. So it may appear to be, if you don't look at the power dissipation, it may appear that you've gotten something for free. All nice characteristics without paying anything. But power is you compare the two things here. The power is what you're paying for. Okay, and as we know, portable applications, this will drain out your battery twice as fast as this one, with current being twice as large as that. Okay, so high performance, many of the times that you'll read, does come at the cost of higher power dissipation, and this is what this is hinting at: higher linearity at the cost of power dissipation. In many other places, you'll see similar kinds of things. All right. There's another benefit of this particular stage here, where you put another benefit that people talk about when you put an RE. And that benefit comes as follows here. Look at this particular stage, our conventional stage. Now, suppose the signal that you want to amplify, the signal that you have coming from whatever source, is 20 millivolt. The signal is 20 millivolt. Right? The input signal is large from microphone or whatever, wherever it is coming from, it's a large signal, is 20 millivolt. If I feed in 20 millivolt into this particular stage, note my output is highly distorted. Okay? So the issue is, if you have to amplify a very weak signal, 5 millivolt, 1 millivolt, it's okay. You can amplify not that much distortion. But if you have a signal which is 20 millivolt, what do I do with it? It gives me very high distortion. What if you had a signal which was 100 millivolt? It's not that I want to amplify only always 1 millivolt or microvolt signal. I may have a signal from somewhere which is, let's say, 100 millivolt. If I take 100 millivolt signal and I apply here, well, go ahead and simulate and see what you'll get. 100 millivolt, apply it here, the output would be totally distorted. Very, very high distortion. So the issue is, how do you amplify a 100 millivolt signal? What do you do with a 100 millivolt signal? I want to amplify a 100 millivolt signal with 10% harmonic distortion. Or let's make it simple. I want to amplify a 20 millivolt signal with 10% distortion. What should I do? Look at this picture. What should I do? I have a 20 millivolt signal and I want to amplify it such that whatever amplification I do, such that my distortion in the output is less than 10%. Well, this is telling you that if you apply 10 millivolt here, then the distortion is less than 10%. But I have a signal which is 20 millivolts, so what should I do? I don't know if a natural solution is coming. If I have an input which is 20 millivolt, why don't I attenuate it, make it 10 millivolts, and then apply it? Does it seem logical? I want to amplify a signal, so what do I do first? I have a 20 millivolt, first I attenuate it. I make the signal weak. From 20 to 10 I make it, and then 10 I feed in here. So I can use a voltage divider and make it 10, and then I feed in 10, then I'll get 10% distortion. Does it make sense that you should attenuate a signal and then amplify it? It doesn't make sense. But remember, every time you attenuate a signal, what would happen is you'll use resistors and all that, you'll add noise to it. You'll add further noise to it. It doesn't make sense. So the issue is, if I have a 20 millivolt signal, how do I amplify that? What do I do? I don't want to attenuate it to 10 millivolt and then amplify. So what do I do? Well, this comes in very handy, this circuit. Why? If you have a 20 millivolt signal, see our small signal analysis that we did, we can calculate the relationship between Vs and VBE. Note that what causes distortion at least most people understand it that way, that what causes distortion is VBE, the voltage that appears across the base emitter voltage here. So the idea is, if you have 20 millivolt, if you can keep VBE to 10 millivolt, right? Are you seeing that this is an attenuator in some sense? Earlier, the entire 20 millivolts was appearing across the base emitter junction. Now this 20 millivolt, some will appear here and some will appear here. We can easily calculate the relationship between Vs and VBE. Vs equal to VBE, 1 plus GMRE. It's a simple relationship that you can derive. So if I put GMRE equal to 1, if I design it like that, then you can see that Vs will be equal to twice VBE. So now if you have 20 millivolt, what this is saying is, if you have a 20 millivolt signal that you want to amplify, put in an RE here, and what happens is 20 millivolt here, make this factor 2, and what happens is base emitter voltage becomes 10 millivolt. So you get a 10 millivolt base emitter voltage. Rather than taking a 20 millivolt here and attenuating it, use this particular strategy. So from 20, you get 10. If you have 100 millivolt signal here, and you want 10 here to appear here, so 100 you can easily calculate, I need a factor of 9 here, and how much resistance do I need to put here? And then you'll be able to apply a 100 millivolt signal here, and you'll be able to amplify that 100 millivolt signal with the similar one. Except that there is a little bit more on it, okay? So for example, I'm pointing out, if you go and read textbooks, the textbook would write something like this. This is from Cedra and Smith. The textbook would write, note that this particular line is talking about this particular stage, and it says that you can extend the input signal by a factor 1 plus GMRE. Note that I said you can extend the input signal by 1 plus GMRE. What it says is, what they are missing, many of the textbooks and many of the discussion is missing, they're saying for the same nonlinear distortion, the input signal Vi can be increased by a factor of 1 plus GMRE. This is wrong. In fact, the stage that we are putting in with an RE there, it not only extends the value by 1 plus GMRE, we also saw what else does it do? It makes the whole amplifier linear by putting a negative feedback. So it reduces distortion also. So this is wrong. This is not true. Example, I have a stage here. We know that if I apply 20 millivolt and I put RE and I get 10 millivolt, I should get 10% distortion. Well, so I took here 20 millivolt, we put 13.5 ohms, and which makes it equal to 2 VBE. So if I apply 20, 10 will appear here. 10 will appear here, and I should, according to the picture that we had, I should get around 9.6% distortion. Same, because base emitter voltage is still 10 millivolt. But what do I get? 4.7% distortion. So this stage, what it does is, it not only, and why it does it is, we discussed last time that base emitter voltage here, this particular signal, this particular circuit, not only if you apply 20, does it make it equal to 10, but this 10 that you see here is not a pure sinusoid. The 10 that you see here is a distorted sinusoid. So that the transistor adds distortion to it, and overall final output becomes a much purer sinusoid here. So this picture is that you can put a resistor here, extend the voltage that you can apply there. You can apply much larger voltage here now, and also get a smaller harmonic distortion. So to summarize, this emitter resistance that you see here not only allows a higher input voltage to be used, but for the same VBE reduces harmonic distortion as well. Okay, so that's a very important point. So you are seeing that a very, very useful small resistor, 10 ohms. In this case, all that we put was 13.5 ohms. Small resistor like this solves a lot of problems. Allows you to get higher input resistance. Allows you to get higher linearity. Allows you to apply a much larger input voltage. 20 millivolt, 30 millivolt, much larger input voltage. Okay. All right. So this is a comparison between the two amplifiers that you see here. If I put 20 ohms, so it allows you to compare the amplifier without emitter resistance and with emitter resistance. You can see what all it allows you to do. Reduce gain, So positive things about this amplifier are what? It allows you to get higher input resistance that you see at the expense of lower output resistance, lower gain here. And the other one is allows you to get higher swing here with comparable distortion.